Well, good afternoon. I'm Warren Hill from Mesa, Arizona, and I have a practice that specializes in anterior segment surgery and intraocular lens power calculations. And today I'm excited to talk to you about some updates we did to the Hill RBF method. We're going to call this version 3. And for those of you who use this, I think you're going to see some improvements that you're going to share my excitement about here. So let's just talk about unanticipated outcomes here, and these are kind of the things that we think about that could happen in times of surgery. They're all common complications, but really the most common complication is an unanticipated outcome, something more than half a diopter, and sometimes even more than one diopter. So I think clearly this is one area where we need to put a fair amount of our efforts to make sure that it doesn't become an issue for you. And really, as anterior segment surgeons, we're being judged by our patients and our peers by our refractive outcomes. We all do, great cataract surgery, very, very predictable 360 degrees of capsule overlap over the lens, nice clear corneal incisions. So this is a differentiating factor from one surgeon and one practice perhaps to another. And just as for way of illustration, let's look at 3,400 cases, and we're going to do a half diopter accuracy calculation here using the SRKT formula. And these are the cases that are outside that half diopter limit. So obviously, we need to do better than something like this. And from the Haggis formula optimization database, which is now approaching 300,000 cases, what we found is that for people who use the more traditional formulas, really less than 1% are at 92% within half a diopter. And I can tell you, each one of these physicians, I mean, there are very, very few of them. At 84%, that's the next level. It's about 6% of surgeons. And really, the vast majority of surgeons are around 78%. And this is a number that we see over and over again, which tells us that it's probably in part driven by technology. So let's take that same database of 3,400 patients, and now I'm going to fit it to an artificial intelligence model, and there's the half diopter error. And you can see right away that this is technology that has us moving in the right direction. So we don't have a lot of time to go into all the details here, but what I'm going to give you is a little primer as to how artificial intelligence works and what it is we're doing. And I'll show you some of the improvements we've made over version 2. And as I mentioned, I think this is going to be very exciting for everybody. So for artificial intelligence, by pattern recognition, here we're using radial basis functions. Facial recognition is a very common application. When I pick up my iPhone, I look at it, it recognizes my face, and boom, takes me right into the into where I want to be. Because fingerprints are a pattern, law enforcement can use this. We've got a couple of metrics. We have both location and we have the angle of the little swirls. And fingerprint recognition by artificial intelligence has pretty much become a standard. And again, if on your iPhone or smartphone, this is another tool for recognizing who you are. And what's an EKG? An EKG is nothing more than a pattern, and this is a pattern called T-wave alternans, where it can indicate a potential for a fatal cardiac arrhythmia. So EKG machines now are using this technology, and they're getting it right, probably even better than cardiologists. So what's the advantage of artificial intelligence? Well, it's termed adaptive learning, because we can optimize outcomes in a very sophisticated manner based solely on data. And current methods limit possibilities to situations that may already be understood, but perhaps incompletely. And manual optimization methods limit the number of solution options. And I think that's one of the key points. This is well suited to real world problems where ideal models are not yet available. And clearly, IOL power selection is one of those. If you take a look at the number of possible combinations for the types of measurements that a modern biometer does, say from plano to -2, that's about 680 million combinations, and no regression formula is going to get all those right. So it's self-organizing. It has the ability to create an independent representation of the data, and it really has enhanced sensitivity for identifying and unraveling complex nonlinear relationships. And this is completely free of calculation bias. It's just the data. So here's something I've shown before, but I think it's worth repeating to give you an idea of the power of this technology. We've got a little square here, and we're going to put 1,000 seemingly random dots inside this square, but they're not really random. They were generated by something called a Manhattan distance generator. And if you were to get in a taxi cab and drive from one point to another, you wouldn't drive through the buildings, of course, you would drive around them, and that's called a Manhattan distance or a taxi cab distance. So we're going to generate these points using a Manhattan distance generator, and we're going to see if a basic fundamental artificial intelligence model can look at this and come up with the underlying pattern. So here's an example of the Manhattan distance driving, block by block around the buildings, and here's the Euclidean distance, the way perhaps a bird would fly. And we're going to give this algorithm or this artificial intelligence model 5,000 cycles to learn and show us what the underlying pattern might be. So here's 40 cycles, not very good. Here's 120 cycles. Here's 500 cycles. And by the time we get to 5,000 cycles, we've identified this as a series of Manhattan distances. So the power of this technology to unravel complex solutions and patterns that are not fully understood is really quite remarkable. So why not do this with IOL power? Okay, so let's talk about how we develop an artificial intelligence power calculator, IOL power calculator, and then we're going to talk about some of the improvements that we made. So first step is, what do we use? Do we use the patient's zodiac sign, mother's maiden name, favorite dessert, axial length, central corneal power, anterior chamber depth, and we came up with 13 different measurements that we thought were useful, including pupil size, 6 millimeter spherical aberration, white to white, et cetera, et cetera. And we used a evolutionary genetic algorithm to do this. So we would make a basic model and we would vary it, and we would do lots and lots of iterations. We would see which candidate models gave us the best outcomes and which factors were important and critical to getting those outcomes. And then we're going to keep doing this over and over again, and we're going to start ranking the various different preoperative factors. And this process gets repeated over and over and over again. And with today's computer, we can do this almost forever until we meet the criteria. And Lee Wong at Baylor University gave us some very specific criteria that we needed. And then we needed to independently validate it. And that validation needed to be at a certain level, so we knew that we were doing a good job. And what we came up with in the beginning was the postoperative spherical equivalent, the axial length, central corneal power, and anterior chamber depth. Now later we've been able to refine this, but this was just our first pass at the process. Okay, so then now we know that we need these items to make a calculator, and then how do we fit this data into an artificial intelligence model to come up with something that we can use? So here we have our data, our fitting data set. We've identified the metrics we need. We run this through our radial basis function, activation functions, and then we compare the differences between what's called the output layer and the fitting model data set. And now we can do a backwards propagation exercise and keep running it through until we don't get any improvement. And that output can become the basis for a calculator. Now, the first thing that we noticed was the output was free of any bias. Remember, this is pattern recognition. This is not a Vergence formula. So whether it's a long eye, a short eye, it doesn't really matter. And we can take a cloud of data, and like we did with that Manhattan distance example, we can take a cloud of data in multiple dimensions and turn it into a straight line. So here's the half diopter accuracy for one of the very first data sets we looked at. And you can see there's really no bias. So that was very exciting. And for version 3, just to kind of get started here, the database that we used for version 3 was expanded over version 2. And for that database, we could fit the artificial intelligence model to within half a diopter at about 99.1% accuracy for that data. So that's a very, very powerful tool. I think we all would agree on that. Now, something else came out of all this that we hadn't anticipated, and some of our engineering friends pointed out that with this type of database and this type of artificial intelligence model, you can also create something called a boundary model. And a boundary model means that we can predict before surgery with a fair amount of certainty what the accuracy is going to be after surgery. So here's a pretty familiar plot, central corneal power against axial length, and we can make a boundary where we know that we have enough accuracy to do this calculation at a 90% level within half a diopter. These are our out of bounds points. So when we do the calculation and any of the data points falls outside the boundary model, we will say we don't have enough data to do the calculation at a 90% level. So let's look at some examples and I'll show you some of the progress that we've made. This is version 1, and these are the 6 pairwise boundary models for 4 preoperative or 4 factors. And so pretty normal eye, a little bit nearsighted. We want to have a plano-spherical equivalent. Axial length is 26 millimeters. Some pretty normal Ks and a normal anterior chamber depth. You can see that each of these points are well within the confines of a boundary model, and that's an inbounds calculation. So when you use the RBF method and it says inbounds, this is really what it means. It says for the 6 pairwise boundary models, we have sufficient data to do the calculation at a 90% level. So let's look at a somewhat different eye. Here's an eye that's a little long, and we're going to go for a plano spherical equivalent. But we've got some inappropriately steep Ks and a very shallow anterior chamber depth. So for this first model with a limited database, it's an out of bounds calculation. We cannot support the calculation at the level of accuracy we're looking for. So now we're going to expand the boundary model and we're going to put in more cases. And this is version 2. So we'll take that same case. We want a plano outcome. It's a long eye, 28 millimeters. Here's our very steep Ks, but now we have more cases. So it converts to inbounds for that because we've expanded the boundary model. And here's our shallow anterior chamber depth. Again, we've expanded the boundary model. So now it becomes inbounds. So with more data, we've expanded the boundary model, and what was once out of bounds is now inbounds. And now we can do the calculation with a predicted 90% accuracy to within half a diopter. So let's talk about version 3, which will probably be available for the online calculator by the time you're viewing this. And this will also be incorporated in the next software cycle of the Haag-Streit LensStar. So here's the expanded boundary model for version 3, and we're going to take a really long eye, 32 millimeters, with flat Ks and a very steep, or very deep rather, anterior chamber depth. And you can see that even though this eye is very, very unusual, it's well within the boundary model for all 4 of these pairwise boundary models. So more and more cases are now available to us for doing the calculation at a known level of accuracy. And we're going to take a really unusual eye. Here's an eye, very very long eye, but we've got some very flat Ks now. And this eye's probably had prior refractive surgery. This is going to be out of bounds because this method isn't working yet for prior RK or LASIK because we don't have the metrics yet that are consistent enough for us to do that. So this would be an out of bounds indication. Now let's compare version 3 to version 2, and we're going to look at 2 extreme examples. Here's a short eye, 20.72 millimeters, and you can see with version 2, the calculation wasn't even possible, whereas with version 3, every single one of the refractive options comes up as inbound. So what we've done is we've greatly expanded the boundary model and given each of us a little bit more options. And here we are for a very long eye, almost 32 millimeters. And you can see whereas version 2 had some limitations, version 3 is greatly expanded for the refractive outcome. Now, this is very exciting. We all know that certain formulas begin to have problems at the extremes of axial length. They kind of become out of their depth. This is where we do majority of our cases, say at around 22.5 millimeters to maybe 25, 26 millimeters. And for most formulas, the power prediction curve is relatively flat, but it may change depending on the Ks or the other values you're using. What we've done for version 3 is we've flattened the power prediction curve from very, very short to very, very long. So those divergences that we see as the axial length begins to change dramatically have been flattened out and modified in a way that I think that's much to our benefit. Now, this is a kind of a ad hoc study we began about 2 years ago, 2 weeks ago, rather, 2 weeks ago. And this is about 9,800 cases from some databases we were able to collect. And we were able to show that that RBF3 actually does do better than RBF2. And we've known all along that RBF2 and Barrett are pretty much indistinguishable at these higher levels, but RBF3 does actually show improvement overall. And that many of these are cases of pooled data. Um, and this wasn't a formal study, but it was just a collection of cases that we had, but we can demonstrate that it is better. So basically, the difference between 2 and 3 is in about 2 years ago, we had 12,400 eyes measured by the LensTAR, improved accuracy for powers up to about 30 diopters, and then the addition of cases from different biometers that allowed us to use meniscus design for IOLs down to -5, and we extended the boundary model down to -5. The expanded 90% half diopter accuracy boundary model over version 1, and we've been very happy with how this has been working. This month, we've expanded the patient database, and it's been refined. So some of the outliers have been removed. We have improved accuracy now for powers up to 35 diopters. We have the incorporation of additional anterior segment values. So that's lens thickness, white to white, and central corneal thickness. And so these three new measurements are used for version 3. If your biometer doesn't have these three measurements, um, uh, the calculation method will do it without the addition of these. We also added gender, and it turns out that if you look at a large enough number of cases, gender does make a difference, but it's a relatively small difference, but we did include that. And as I showed, the 90% half diopter accuracy boundary model has been expanded for this, giving us all some additional options for the refractive outcomes. So what's the future of lens power calculations? Well, we're really having a convergence of different technologies for IOL power selection accuracy. It involves ray tracing, artificial intelligence, of course, advanced versions formulas like the Barrett Universal 2 formula, and also interoperative aberrometry, which has some value, especially for the toric IOL, for the magnitude and alignment of that lens. Um, but I think going forward, as we all work very hard to push the boundaries for calculation accuracy, the method with the greatest sensitivity and flexibility is going to have the best accuracy as our measurement technology advances. And right now, we're kind of coming up against a wall in terms of measurement accuracy, with keratometry being something we're going to have to improve as the years go by. So right now, 78% is tolerable. That's a number that we see very frequently as I look at databases from different physicians. 80 to 84% is acceptable, and that's kind of the next level up. I think 90% is achievable by really taking a lot of care with how you do your measurements and using modern biometry. And we optimize the ocular surface on every single patient prior to undergoing biometry, and that has really helped improve our accuracy. And the future, I think, we're looking at 94% perhaps for the next generation of measurement technology and further improvements in artificial intelligence. So just to review, that's 78%. That's kind of where a lot of people are right now. And really, I think we need to do better. This is 90%. Here's 94% where I hope we're going to be going in the next few years. And really, the point of this project is nothing less than making it so that the spherical equivalent no longer becomes an issue as we do the best cataract surgery that we know how to do for all of our patients. And thank you very much.